In this video, I'm going to talk about formal charges and how you can use them to determine the most favorable resonance structure for various compounds. So first of all, let's do some definitions. So what are formal charges? So formal charges are effectively the charge felt by each individual atoms within a molecule. Right? So basically, if an atom has, so we have to calculate formal charges for every individual atom in a molecule, and effectively, you can think of that atom having that specific charge completely by itself. Now, resonance. So resonance structures are basically structures of the same molecule with different locations of electrons. So for instance, these three structures I have shown right here. So these are all the same molecule, and there are three resonance structures of that same molecule. So the only difference between resonance structures, you can't change the connectivity, so you can't change what atoms are bonded to what. So for instance here, I couldn't all of a sudden now draw a new structure where nitrogen and sulfur are bonded together. All you can do is move around lone pairs and some bonds from double or triple bonds to kind of change the way that the electrons are located. Now, all of these are acceptable structures based on the rules I laid out in the Lewis structure video. And so this is the reason why we need resonance, is because the way that electrons actually behave in the real world is not the way we see it in Lewis structures. Lewis structures are a convenient way of mapping what's called areas of high electron density. So basically, electrons are moving around very, very fast all the time. Right? They're constantly moving throughout the entire molecule. But using quantum mechanics, we can actually calculate areas that they are most likely to be at any one given time. So for instance, if I were to freeze time on the molecule, we know areas within that molecule that electrons most likely will be, because they spend the majority of their time there. Those areas of high electron density, if they're in bonding orbitals, which is a concept I'll touch a little bit on next chapter, we show them as a bond, and if they're in non-bonding orbitals, we show them as a lone pair. But some molecules, like this one for instance, have different perfectly plausible ways that those electron densities could be mapped out. So we need to draw resonance structures. Now, these do not mean that this molecule flips back and forth between these three different structures. What it actually means is that the true electron structure is some kind of hybrid average of the three of these. Okay? Now, if you have resonance structures, the way you indicate that they are resonance structures is you just draw a double-sided arrow between them. Right? So that means that they're resonance structures. Now, when I say hybrid average, what do I mean by that? Well, so basically it's a weighted average. So we have three different resonance structures here, but they don't always contribute to the overall structure perfectly evenly. Sometimes you have a more favored structure than others. And in order to figure out the most favorable structure, you have to know the formal charges. So how do you calculate formal charges? Formal charge, so I use an equation that's a little bit different than what you'll often see in textbooks, but I personally think that mine is simpler, so I'm going to teach it to you this way. So the formal charge equals the number of valence electrons minus what I refer to as the number of associated electrons. Now, what do I mean by an associated electron? Basically, any bond that's touching an atom contributes 1 electron. So remember, bonds have 2 electrons. You can think of 1 of the electrons going to each of the atoms that bond is between. And a lone pair, each of those electrons just count towards whatever atom you are, or whatever atom it's on. Sorry. So basically, for this number, just count the number of lines and dots that are touching that atom in the Lewis structure. So, for instance, let's look at this first version over here. Nitrogen. Well, the number of valence electrons, just as in the last chapter, you get that from the periodic table. So remember, nitrogen has 5 valence electrons. So we'll put 5 minus the number of associated electrons. Again, count every line and dot that touches nitrogen. So we've got 1, 2, 3, 4, 5, 6, 7. 5 minus 7, nitrogen has a -2 formal charge. Carbon. Carbon has 4 valence electrons, which again you get that from the periodic table. Count every line and dot. There are no dots, no lone pairs, so just count all the lines. 1, 2, 3, 4. 4 minus 4, no formal charge. Now, if you're asked to indicate formal charges, you often don't have to put a 0 if there is no formal charge. So if it doesn't explicitly say to include it, you often can just include formal charges that are non-zero values. But for the sake of right now, I'm just going to write it in. So sulfur, looking on the periodic table, it's right below oxygen. So that it has 6 valence electrons. Now it's got 1, 2, 3, 4, 5 associated electrons. So it has a +1 formal charge. So now let's do the same for the other two. Nitrogen, again, 5 valence electrons, and we've got 1, 2, 3, 4, 5, 6. So 5 minus 6 is -1. Carbon still just has those 4 bonds, 0. Now sulfur, 1, 2, 3, 4, 5, 6. So 6 minus 6, sulfur now has a 0 formal charge as well. Now let's look at this last structure. We've got nitrogen, 5 minus 1, 2, 3, 4, 5, 0. Carbon still again just has 4 bonds, 0. Now sulfur is 6 minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7, -1. Okay, so how does this tell us? Sorry, I shook the table there a little bit. So how does this tell us the most likely form or structure? Well, the first thing you want to look at is you want to try to minimize the formal charges as much as possible. If you can, you would want all the formal charges to be 0, but that's not always possible. And in fact, if you have a charged molecule, you know it can't be possible because the formal charges of all of the individual atoms have to add up to the total charge of the molecule. So we see -2 plus 1 is -1, and then each of these two just have a -1. But try to get them reduced as much as possible. So this structure here on the left has certainly more non-zero formal charges than these other two, so that's going to be our least favorable resonance structure. Again, it is still a plausible resonance structure, but it would contribute the least to the weighted average. Now, these two. So if you can't pick the best one just from that, which again here these each have just one non-zero formal charge, and it's the same one, -1. So there is no differentiation yet. If that's the case, you want to choose the structure that puts the most negative formal charge on the most electronegative atom. So between nitrogen and sulfur, nitrogen is more electronegative than sulfur, so that one is going to be better at holding on to this negative formal charge. So this would be our most favorable resonance structure.